subsystems. We start with decision making the AI decide what to do. And then there's fact finding. It's a big, complex subject that deserves category on its own. And then there's situational awareness, where you let the AI know things about the world. So this talk only focuses on decision-making systems, and we usually implement that with a finite-state machine. So what's a finite-state machine? It's the idea that your AI character has this sort of different modes of behavior. So when you play stuff like RTS games like StarCraft, di mo mapapansin yung merong button doon na guard stance, aggressive stance, and based on that, nag-iiba yung behavior niya. So that's what they do. So based on that, mag-iiba yung behavior niya, and nag-a-adapt siya according to events in the world. So usually the AI has some sort of control mode where it moves back and forth between two positions, and then pag may nakita siyang enemy, it's going to move to attack mode where it's going to pursue that enemy. And then if, let's say, kung mahina na siya, it goes to retreat mode where it tries to evade that enemy. And pag sinabi mong state machine, it's usually all about state transitions where you check for a condition kung kailan siya mag-move from one behavior to another. And we usually do this to manage the complexity of the AI. You can segregate their behavior into different modes. So, problem lang with that is the more you build bigger and bigger FSMs, finite-state machines, ang hirap ng basahin, especially when you get to larger scale state machines like this. So if you ever experience something like this, I'm here to inform you that there's alternative systems out there na mas madaling i-manage. So what's the other usual way to implement AI? Usually you use scripts like, I'm talking about scripts like Lua or Python. Basically, you're adding another programming language on top of your game. And the nice thing about it is it's Turing complete, meaning to say, if you have some sort of weird plan for your AI's behavior, it's most assuredly na kaya niya ng script. The problem now with scripts, it's difficult to use for non-programmers because something like designers, they get caught up in the little details like the syntax. And it's hard to give your AI a sense of planning ahead. And with state machines, that's a problem. So it turns out the academe has been at this problem too for a long time because they're doing stuff like robotics and virtual reality environments. So some of the stuff they do medyo applicable din to video games. And one of the things they did was what they call planners. So the idea with planners is very simple. It's an idea of a system where your AI detects that it's existing in a world where it's a state of the world where it doesn't want to be in, and it does some steps a little bit at a time to get to the state of a world where it wants to be in. So, for example, here's Bob. He lives in a world where Bob equals hungry, so he does something, some plan to get in a world where Bob equals not hungry. Fear. Sinong nakalaro ng fear? Yeah. So, fear had a very advanced AI for its time. It released in 2005. It had behavior like AI diving into cover, throwing grenades to flush out the player, and diving through windows. And before its time, parang siya lang yung game na ganun yung behavior ng enemy. So fear actually uses an FSM, and guess how many states there are in their FSM? 1,000. Okay, I'll show you the FSM that fear uses. Yan lang. It's just 3 states. So it's weird. Paano nangyari 3 states lang and the enemy can dive through windows, flush the player with grenades, and even communicate with their teammates. But it turns out, yung FSM na yan is just used to facilitate movement and animating the enemies. So it's not really used as the AI. The AI part was really done by a planner system. So this is Jeff Orkins. He's the single person who created the AI system for fear. And when he was about to create the AI for fear, he didn't choose to use FSMs. He saw the planner concept that the academy made. And he thought to himself, baka pwede itong i-apply to video games. So that's what he did. He created a system. He called it GOAT. It stands for Goal-Oriented Action Planning. So what's GOAT? I'll explain it with an example. It's easier that way. So let's say you have an enemy over there. He doesn't have any weapons yet. There's a gun on the ground, and there's the player. There's the player over there. So what happens is it starts with the developers assigning the enemy what their goal is. So for example, the developer says, yung enemy, kill the player. So what happens is, yung enemy, it's like it's going to put up a post-it note on itself, like a to-do list. So it's going to put kill player at the end of a list. So let's say that list is over there. So what's going to happen then is it's going to look at its list of abilities that it can do. Usually in state machines, your AI has states, but in Go, your AI has actions, what it can do. So for example, in our hypothetical game, our enemy AI can do this stuff, shoot at player, pick up a gun, move to a destination, take cover, and so on. So what it does is it just picks which action can give the desired effect. So it just so happens that the shoot at player, the effect that it does, it actually kills the player. So makakonect na yun. He needs to kill the player, and shoot at player action can achieve that goal. So what it does is it's going to connect that shoot at player into the kill player in that list. But that shoot at player actually has a prerequisite that it needs to satisfy. For example, the shoot at player needs, the prerequisite is it needs to have a gun on hand, and it needs to check, does he have a gun on hand? And if it's not, and if it turns out it didn't, it has to go through its list of actions again and find the action that will satisfy that prerequisite. So for example, it just so happens that the pickup gun ability can give that desired effect. So kumbaga, the end goal is kill player, but because of that prerequisite, he has a new sub-goal of having to find the gun. So mag-chain lang yan until he can find an action whose prerequisites he meets. So for example, finally, you nakuha na niya. So what do we have in the end? We have a list of steps that the enemy can do to finally kill the player. And if you think about it, hindi na natin kailangan i-hardwire yung state transitions. Siya na bahala nag-combine ng steps na to para magawa yung goal niya. That's what Go does. It's all about upfront planning. It's about, excuse me. anticipation. It's all about deciding what to do before it starts doing it. So by that nature, it just so happens that sometimes the enemy AI can actually think of more than one plan to achieve this goal. So for example, here, he can maybe get a gun and shoot the player, or he can backstab the player, or he can ambush the player with bombs. And they all achieve that common goal of killing the player. So it gives your AI some amount of unpredictability. It's making the AI a bit crafty and resourceful. And that also makes it easy for you to create different types of enemies. Like if you want a melee type of enemy, then you only give him melee type of actions, or range attack enemy, you just give him range attack options. And well, with that, the fact that it can create many plans, the problem then is which plan should you choose? So the easy way to do this is just, if I go back here, the easy way to do this is just assign a cost to each action. And what it simply does is just something it makes a total of all the costs for that whole plan, and just picks the one with the least expensive plan. So for example, you give each action a cost, and it's pretty much up to you what amount of cost you give to each action. It depends on your team. And if you think about it, you can use classic A-star algorithm to make the AI pick the best plan. Think of it as you're giving an F score to all these actions, and then your H score would be some sort of upper limit to, let's say, pick a plan that is not beyond 500 cost units. So more than just giving your AI preference, it's about optimizing how he formulates his plan. So what happens is it's going to cull out formulation of plans that may be too costly. So here are a list of games that, since the release of Fear, other games actually adapted the use of Go. You see here Stalker, Fallout 3, and Empire Total War. And these last two, they actually made AI systems that, well, it's different from Go, but it has its roots traced back to Go. So for example, in Fallout 3, it can happen that maybe you're killing these two super mutants, and you killed one, and what can happen is the other super mutant can decide that, hey, that my dead comrade's weapon is actually better than mine, so I'm going to drop my weapon, pick up my dead brother's weapon, and use that against the player. So in typical FSM, you wouldn't have thought something like that, but in Go, that's pretty much natural. In Empire Total War, one of the devs of Creative Assembly said, the Go is like a state machine that rewrites itself. And that's pretty much a good description. And here's one of the excerpts of an interview. This says they actually use Go. So far, I've painted a pretty picture of what Go can do, but it also has its problems. One of the problems is it's flexible, but it can be too flexible. Say, for example, you want a linear scripted cutscene that you want your AI to just do one thing and one thing only. It's going to make it difficult to use Go, because by its nature, Go likes to diverge and do different kinds of stuff. So for example, in one scenario, the guys who made Killzone 2 guerrilla games, they started actually using Go, but they decided later on to use a different kind of system because it was just too let's say, random. So for example, in one of their situations, they wanted a boss fight that had predictable patterns. But using Go, that was difficult. So they actually use it. They actually use a different planner system. It's still a planner, but it's different. They call it HTM planner. It's called hierarchic task network planner. And one of the other problems with Go is just let you watch that. Okay, my only point was that it's difficult for a Go system of AI to employ the use of backup plans. As in, if plan A didn't work, then use plan B. It's difficult with Go because if you remember what I said was with Go you can use A star to make it choose the best plan. So it's going to be difficult if you consider the permutations and the branching out. If you're going to store all that, especially in a video game where frame rate is important. So let me just recap. Here's on one side you have finite-state machines. On the other side you have Go planners, or sorry, I forgot to mention. Go, it came from this system that Stanford Research University created. They call it STRIPS, Stanford Research Institute Problem Solver. It's where Go came from. Basically, it's just Go was it's pretty much STRIPS but adapted for video games. So finite-state machines think in terms of adjectives, being aggressive, being suspicious, maybe being cowardly, and Go thinks in terms of verbs, thinks in terms of end goals. They think in terms of like a to-do list, like getting things done. Finite-state machines are predictable. They lend themselves well to linear games. And Go, by its nature, is unpredictable. They lend themselves well to open-world sandbox games that have emergent gameplay. And finite-state machines, they focus on adaptiveness. They're very event-driven. And Go, on the other hand, they focus on anticipation and planning ahead. And by the way, the other problem with Go is, say for example, go back to the earlier scenario. Say that's his plan. So he's going to pick up a gun and use it to shoot a player. So what if in the middle of him getting the gun, maybe the gun exploded into pieces? So mangyari useless na yung plan niya. So how do developers cope with that? What they just do is they force the AI to reformulate its plan every other second or so. So what in theory sounded like an elegant solution, it turns out to be a brute force approach. So I'll just go back. So, is there a way we could get the best of both worlds where the adaptiveness of finite-state machines with the idea of planning ahead with Go? And you'll see later on, the more they optimize these two systems, the guys who like to use FSMs, the guys who like to use Go, the more they optimize it, the more they converge into a single common idea. So, for example, the optimizations on finite-state machines, what did they do? They did the idea of composite states where you group states together, or like a sub-state machine where you have an FSM inside an FSM, or maybe they like to call it a hierarchic FSM. So instead of having to deal with this, which is pretty much unreadable, you just deal with this, where your states are in like folders. So it's easier for you to manage. So you can just zoom in and you see subfolders, and if you zoom into the tiniest detail, you can see finally you can see the low-level states. So that's one of the optimizations they did. You can just zoom in into the tiny details. So the idea now is you have a high-level view of your state machine where the low-level details are abstracted from you. And on the other side of the fence, the guys who use Go, they also optimized it. What did they do? They did what you call composite actions. It's very similar to what the guys in state machines did. They group together actions that make sense to be done together, so the AI doesn't have to do a search anymore. And they added a hierarchical structure to their planners where you start with your end goal and you break it down to sub-tasks, sub-goals, and then you further break it down. So this is what actually a hierarchic task network is. That's what an HTM planner is. That's what Killzone 2 uses. So we're starting to move away from the idea that Go, where the AI searches by itself what plans, what series of steps to do, and they're bringing back more manual, hardwired transitions by the use of the hierarchy. So again, you're seeing the idea that we're having a high-level view of our AI system where you can zoom in to tiny details. Excuse me. So I'm just basically explaining that we're moving away from quirkiness of Go, that's stubborn, that stubborn uses Go. And we're using now systems that have more controlled structure like HTM, hierarchical task network. Those are some of the games that use HTM planners. Killzone, presumably the newest Killzone PS4, they still use like HTM planner. They use Armed Assault. If you guys play Arma 2. They actually use planners to formulate mission scenarios in Arma. And the recent Transformers game, they also use HTM planners. So there, like I said, there's a trend that even though people are using different AI systems, they see the value of having a high-level view of their system where you can zoom in and out as you please. So again, on one end, you have your finite-state machines. They're reactive, they're adaptive, they're very event-driven. And on the other end, you have your planners. They like to start with a goal and work their way backwards from there. And I'll just include here scripting, where it's Turing complete. It's very expressive. If you have some sort of weird desire for what your AI behavior is, it's much easier if you just script it in. So over time, the developers who use these systems, they actually tend to cross-pollinate ideas with each other, and they start converging on a common system, and they call it behavior trees. So behavior trees, there's a term of behavior trees in software engineering. I'm not talking about that. I'm talking about behavior trees in the context of video game AI. So behavior trees started by a developer in Bungie called Damien Isla, and he started it with Halo 2. But back then, it wasn't really called behavior trees yet, because, like I said, behavior trees started out as they took ideas from different AI systems. So behavior trees, they combine these qualities from other AI systems. They took the goal-oriented idea from planners, where you start with a goal and you work your way backwards from there. They took the idea of being adaptive from state machines, where if a sudden change in the world invalidates your plan, you can use a backup plan. And they use, from programming languages or scripts, they use the idea of custom logic flows. Later on, when I describe behavior trees, you're going to see they kind of look like visual programming. So behavior trees, they do all that, but they're not a silver bullet. It's more like they're a jack of all trades but master of none. Behavior trees, they don't do goal-orientedness or adaptiveness as good as those other systems. But all things said, it's still a good bang for a buck. So behavior trees, visually speaking, they look like this. They look like HTML planners. And if you've played Dragon Age, if you played around with the tactics screen, it's more or less, you're more or less one step closer to understanding how behavior trees work. So you can see there, I'm sure you can see there. It's very simple the way they do the AI in Dragon Age. It's just one long if-else-if chain where you can drag and drop the different actions and conditions. So behavior trees, they look like this. You start with a root node. It's pretty much a tree structure, and you traverse it like a tree. So it starts with a root node, that's the entry point, and you have your branches. All they do, they're just simply like folders to just group together the actions. And finally, your leaf nodes, they're the actual actions. They're the things that actually do stuff. And there's two types of leaf nodes. There's the condition nodes, I like to call them query nodes, where they just query for information from the world. They're pretty much read-only stuff. And the actual actions that actually do stuff that outer the game environment, like attack, defend, or pursue. And conditions are more like true or false checks, like is my health below 50%, or is there an ally nearby? And as for the branches, there's two types of branches. There's sequences and there's selectors. And sequences, they're pretty much what you might think. They're just sequence of actions grouped together. So for example, I have here a brush teeth sequence. So let's say, for example, we're making a Sims clone. So basically, you have your brush teeth sequence, and the children of that node, of that sequence, are just the steps that you do to complete brushing your teeth. So basically, it's just like planners where you start with your end goal and you work your way backwards from there. So they're simply the children are the steps you need to complete that end goal. So if you execute this sequence, what's going to do is start the sequence. It starts with the leftmost, the first child, and it executes that. Let's say the first child is a condition where it checks if my teeth need brushing. So it returns a true or false check. If it returns true, then it moves to the next child. Say the next child is, instead of just a true or false check, it's actually an action. So what it does is it needs to execute that action, and it has to wait for it to finish doing that action. So maybe it has to do a walking animation, so it has to wait for several frames for it to finish. So what that means is it's going to have to suspend executing the behavior tree. So once that go to bathroom action finishes, it's going to report if it succeeded or failed. So meaning, say, if it succeeded, then it finally reached the bathroom. Maybe if it failed, then maybe it couldn't find the path to the bathroom. So let's say it succeeded. So what it does, it just simply goes through each action until it reaches the final child. Then when the final child reaches success, it goes back to the parent node. Then it also reports success. If at any time one of the child nodes reported an error, then what it does is it just bails out. Just like an early out of board sequence where it's going to skip doing those last two children nodes. Because it doesn't make sense to try doing them anymore. The second node failed. So it doesn't make sense to try to brush your teeth if you can't go to the bathroom. So in this way, you could think that behavior trees, error checking is an integral part of the system. And here, selectors let you choose different ways to achieve a common goal. So for example, you have a clean mouth goal. It's more high level, it's more abstract than brushing your teeth. So again, you start with your end goal, which is to clean your mouth. And the children, in this case, instead of steps to complete that goal, it's just different ways to achieve that goal of cleaning the mouth. So if you see the brush teeth sequence is over there, it just means brushing the teeth is one way to achieve that goal of cleaning the mouth. So how does it work? If you execute the selector, it just goes, just like the sequence, just goes to the first child. If the first child failed, then it's going to jump to the next child, and it tries that. Because it tries its best to find a sub-tree that actually achieves its goal. So once it finds a child that reports success, then it's going to bail out and report success. So it doesn't need to do that last action because it already achieved its goal. So in this way, you can think of selectors as a way for behavior trees to do, if plan A didn't work, then let's do plan B. If plan B didn't work, then let's do plan C. So you can think of sequences and selectors as they're like and/or operators. They pretty much complement each other, and if you have something you want the AI to do, chances are you can express them by a combination of sequences and selectors. You just chain them together. And there's one last type of branch node, we call it a parallel or a concurrent, where if you execute a parallel, it just runs all the children simultaneously. So for example, here I have a sub-tree called aggressive behavior, and one of the children is movement and the other is shooting. So you can think of here where it executes moving and shooting at the same time. So you can, this one way you can execute run and gun behavior, shooting and running at the same time. So the parallel will just wait for all of them to finish. It might not be all at the same time. So once they finish, it decides what kind of return value it gives, if it gives success or failure. One of the things you can do is make it strict, as in it will return success only if all of the children return success. Or you can make it lenient, where if at least one child returns success, then it's okay. It returns success. You can have it that you implement both, and you just have some sort of setting in your parallel node which one you want to use. So this is usually where you employ the use of multi-threading. If you can't, for some reason, implement multi-threading in your game, you can still achieve this by doing what operating systems do back then where there wasn't multi-core, and operating systems still manage to run multiple programs at the same time. Because what they do is, they do this, what they call time slicing, where you run one program a little bit, then pause it, go to the next program, run it a little bit, pause it, go to the next program, and so on and so forth. So you can achieve some sort of concurrency, even though you don't have multi-threading. And if that's not enough, there are even more tricks you can use to control the logic flow of a behavior tree. We're going to borrow a design pattern idea from software engineering. They call it decorators. So for example, I have here a melee attack sequence where it checks if it has target, then it does a sequence of attacks like act, slash, and spin attack. So what I'm going to do here is I'm going to add a loop decorator in between the hack. So what it does is it's going to do the hack 3 times before it goes to the slash action. So if I show it here, it's going to move the first child, it's going to move to the loop. It's going to do the hack once, then it goes back up, it checks the condition is to loop 3 times, so it only performed once, so it's going to go back and run the hack again until it achieves the required amount. So once it achieves the required amount, it goes to the next child. this is one way you can override the logic flow of your behavior trees. You can even put loops on top of whole sequences, so you can make repeats of a whole sequence or a whole selector. So in this way, behavior trees are very quite modular, where you can drag and drop stuff anywhere you want. And some other examples of decorators, you can have a breakpoint decorator, where if the execution reaches that, it's going to pause. It's useful for debugging. Or a semaphore decorator, if you can to synchronize parallels. Or you can use some sort of modulating decorator where you force a subsection of the tree to run only, say, 5 times per second. Here's some example of games that use behavior trees. Like I said, it started with Halo. Started Halo 2 and Halo 3. And Crytek, for some reason, they love behavior trees, so they used it in all their Crisis games. And it's not all just violent video games that use these AI. For example, Sport, they use behavior trees also. So, in closing, I explained to you many kinds of AI systems like Go, HTM planners, and behavior trees. But it still depends on the situation what you should use. I'm not saying that behavior trees are the best and everything. So it still depends on the situation. Use the right tool for the right job. And what I showed you here are only the tools. It's still up to you how good you are at using those tools. So even if you use behavior tree, that's not going to guarantee superior results. And as Playmaker proves, Playmaker is this plugin in this game engine called Unity, where it's simply a state machine. It's a visual drag and drop editor for state machines. But the nice thing about it is you can use it not just for AI, you can use it to code your whole game in just that state machine. So it just proves that AI systems, you can use them not just for AI, you can use them for different stuff like maybe cutscenes or dialogue trees, or even like that logic for your whole game. Here's one website I can recommend, AIGameDev.com. They have very nice articles about video game AI. And that's about it.